We'll work a few review problems here to get ready for the test. So on the first ones here, we're going to find the limit or state that it doesn't exist, and then show the work that justifies our answer. So on the first one, the limit as x approaches -4 of the absolute value of x plus 4 over x minus 4. We have a couple of ways we can do this. If you remember what the graph of y equals absolute value of x over x looks like, that is going to be anything positive, and we get the absolute value of x over x, which is the same thing. Absolute value of 5 over 5 is 1. Absolute value of 10 over 10 is 1. So it's going to be a horizontal line at 1, except that it's going to be undefined at 0. And any negative value is going to be -1, because the absolute value of -3 over -3 is 3 over -3, which is -1. Absolute value of -100 over -100 is going to be 100 over -100, which is -1. And then what the, oops, and I did this wrong. Let me make that a plus, oops. I'm going to change that real quick. That was intended to be a +4. Sorry about that. So this is really just that graph translated to the left. So that would be one way to identify that. And so this would become the value x equals 4, where the jump occurs. And we would have left-hand limit different than right-hand limit, or you could say the left-hand limit is going to be -1 and the right-hand limit is going to be +1. You could also plug in very small numbers. So if you said x was, say, a -3.9, that would be a number just to the left of -4, and you would get the absolute value of -3.9 plus 4 over -3.9 plus 4. And you could see then that you're going to get the absolute value of 0.1 over 0.1, and see that that is going to be, oops, so that's going to be equal to 1, and that's as you're coming in from the right. So that would be a right-hand limit, because -3.9 is to the right of -4. If you use -4.1, then you would get -4.1 plus 4 in absolute value over -4.1 plus 4. That would be the absolute value of a -0.1 over a -0.1, which you can see would be giving you a -1, and that's going to be our left-hand limit. And so there's another way of getting to the left-hand limit is not the same as the right-hand limit. Therefore, the limit does not exist. Okay, on the other one, a little bit trickier. We're going to have to be clever. If we plug in 0 directly, we get 0 over 0, which is indeterminate. So we're going to notice that that denominator, we can factor out an x squared, and hopefully that's suggesting we can get like a sine x over x kind of option. So we can take this and tease it apart. So we could think of that as being sine 5x over x times sine 2x over x times 1 over the 2 plus x. Then we can, trying to make these denominators and what's inside the trig function, the sine function, look the same, approach 0 at the same rate, we can multiply here top and bottom by 5, and here we can multiply top and bottom by 2. That would allow us to leave that 5 in the numerator outside, but bring that 5 in the denominator to join the x to make these, the sine 5x and the 5x in the denominator, approach 0 at the same rate. In a similar fashion, we can bring the 2 from the 2 over 2 into the sine 2x over x and leave the rest the same. So now as x goes to 0, when we take this limit as x goes to 0, this, whoops, didn't mean to erase that. So let me put that back. Because these are the same, they are going to approach 0 at the same rate, and these limits will go to 1. And so we're going to get the 5 from here times 1 from there times another 1 from there, times the 2 from here, and then direct substituting in 0 there is going to make that be a 1/2. And so at the end of the day, we're going to get our limit is 5. Kind of crazy, but kind of fun. So the next one, if we direct substitute in 4, we're going to get 16 minus 5 is the square root of 11. And then 2 times 4 is 8 plus 3 is square root of 11. And so we're going to get 0 over 0, which is indeterminate. So our trick here is going to be to multiply top and bottom by the conjugate. So we're going to take this x squared minus 5 in the radical, the 2x plus 3 in the radical, the x minus 4, and we're going to multiply by that conjugate. So x squared minus 5 plus the square root of 2x plus 3 all over square root of x squared minus 5 plus square root of 2x plus 3. I'm going to have to change this. Let me change this because otherwise we're going to get something that is going to be undefined. No, we're going to be okay. I'll take that back. We'll let it roll. So in the numerator, a minus b times a plus b is a squared plus b. So we're going to get x squared minus 5 minus the 2x plus 3. In the denominator, we're going to just be patient. Let that x minus 4 hang out, and we'll have our square root of x squared minus 5 plus the square root of 2x plus 3. That's just going to wait down there. So in the numerator, we get x squared minus 5 minus 2x minus 3. I'm just going to leave that denominator as it is. So in the numerator, we're going to get x squared minus 2x minus 8. Still got that same stuff down there. This is good news because now that numerator is going to factor into x minus 4, x plus 2. We have the x minus 4 that's been patiently waiting its turn down in the denominator, and we still have that square root of x squared minus 5 plus the square root of 2x plus 3. And now we're ready to take that limit as x approaches 4, but we can cancel the part that was going to give us 0 over 0. Now when we plug in 4, we'll get 4 plus 2 in the numerator, so that looks like 6. We'll get 4 squared is 16 minus 5 is the square root of 11. And then we'll get another square root of 11 out of that. That's 6 over 2 square root of 11, or 3 over the square root of 11. Probably what you would have guessed when you just looked at that originally. All right, on to the next panel. Let's see what we got here. So here we want to know where is the function discontinuous, and then what kind of discontinuity does it have. So if we notice that we can factor an x out of that denominator, and now we can see that it is possible for these 1 minus x and x minus 1 cancel to leave a negative 1, that tells us we have a hole in the graph at x equals 1, and we know that a hole in the graph is a removable discontinuity. So that is going to be a removable discontinuity. In the meantime, that x is still surviving, so negative 1 over x, because that x makes the denominator 0, but it doesn't cancel with the numerator, that means it's going to be a vertical asymptote, which we call an infinite discontinuity. So there's a removable discontinuity at x equals 1 and an infinite discontinuity at x equals 0. Now, what we're seeing in the green g of x is a version of our sine of 1 over x. So somewhere in the back of our mind, we know that as x goes to 0, this 1 over x goes to infinity. And when we try to imagine what happens with sine at infinity, we get all of those infinite number of waves that all get condensed around 0, and it's going to be an oscillation. So what happens with our sign of 1 over x plus 1 is that oscillation has been translated to x equals negative 1. Then that is going to be discontinuous because the limit doesn't exist, or we can just say because it oscillates, which is why that limit doesn't exist at x equals negative 1. Now on the blue one, if you imagine what's happening here, as we approach 1, we know this left side here, x squared is a parabola. So it's coming into at 1, it wants to be 1, so it's heading in towards that point 1, 1. Meanwhile, this x plus 1 is just a straight line, but when you plug in 1 for x, that's going to be 2. And so there's going to be a solid dot there. It's going to have a slope of positive 1, so it's taking off going here. So that's telling us that that limit as x approaches negative 1, as x approaches positive 1, we're going to see that we have that's not going to exist, but we're talking about discontinuity. We can see this is going to be what we call a jump discontinuity. Since we're coming in towards different points as we come in from the left and from the right. So the next one here, we're supposed to evaluate f prime of a using the definition of the derivative, limit as x approaches a of f of x minus f of a over x minus a, and they want us to use that to evaluate f prime of 7. So that's telling us that our a is 7, and here's our function. So we are going to take the limit as x approaches 7 of, and f of x is going to be the square root of x minus 3, minus f of 7 is going to be the square root of 7 minus 3, which is the square root of 4, which is 2. And so that's going to be over x minus 2. So if we try to, over x minus 7, because 7 was our a. So as x approaches 7, in the numerator we get the square root of 4, which is 2 minus 2 is 0, and the denominator is also 0. It's going to be indeterminate. So the way we will resolve this is, again, we are going to multiply top and bottom by the conjugate, a tried and true strategy. So we will multiply by the square root of x minus 3 plus 2. So in the numerator, that'll give us the difference of 2 squares. And so that's going to become the radical gets squared and gets removed, and then a minus 4. And we're going to get our x minus 7 that will just hang out while we wait to see what's going to develop up in the numerator. And the square root of x minus 3 plus 2 is waiting in the wings as well. These are, the numerator is going to combine to be x minus 7, which will then cancel. Then we are free to take that limit as x approaches 7, and that will make this a 1 in the numerator, and we'll get the square root of 4 plus 2, which is 2 plus 2, which is 4, and that is going to be our f prime of 7. All right, on to the next panel. So here, where did I go there? Oops, I didn't want to do that. I hit the wrong one. So here's where I wanted to be. So here is, now we're going to try to state the value of x for which f of x is not differentiable, and then tell why. So by why, I mean, is it a corner, is it a cusp, is it a vertical tangent, or is there a discontinuity there? So in the first one, what we're trying to see is this 7th root, and this cube really means that's x minus 2 to the 3/7 power, and the plus 1 is just kind of a distraction. So we are supposed to remember that odd over odd is a vertical tangent. Remember, our kind of exemplar is going to be that cube root of x, which has a vertical tangent at 0. And that's a 1/3 power. So we are going to have a vertical tangent, and that is going to be at x equals 2, because of the translation. So it's not differentiable at x equals 2 because of the vertical tangent. Now, the next one's kind of tricky because we have an absolute value inside of a cube root. So what happens is, without the absolute value, let's just take a look. Without the absolute value, we would have, at 1, we would have this cube root happening something like that. We'd have that vertical tangent. But what the absolute value is going to do is take anything that is negative and kick that up above to make it positive. It's going to reflect it up here. So what the effect of that absolute value has is it changes what was a vertical tangent into a cusp. And so at x equals 1, there is a cusp. That's a new twist on how to get a cusp. So on the next one, here again, we're supposed to notice that we have exponents of 2 and 1/3. So that is saying that this is x plus 3 to the 2/3 power. And so again, even over odd is a cusp. And because of the translation, we're going to have this place where the function is not differentiable at x equals -3. And that's going to be our sort of traditional cusp. All right, very good.